Imagine holding a pen. You press it to paper, and thought becomes real. Black liquid flows from your hand, and suddenly an idea that existed only in your mind now exists in the world. This seems normal, but it's completely insane. Wouldn't it be simple? Just find some colored water and you're done? Well, no. Water evaporates. It fades. It washes away. The story of ink is the story of humans desperately trying to make thoughts permanent, and we had to invent chemistry to do it. Let's start at the beginning. Early humans had a problem. They had thoughts worth remembering, but thoughts disappear when you die. So around 40,000 years ago, someone ground up red rocks and mixed them with fat. This made paint for cave walls. It worked, but you can't carry a cave wall with you. You need something that flows, something liquid that dries permanent. The first real ink appeared around 2500 BCE in Egypt and China, independently at the same time, which tells us something important. When humans reach a certain complexity, they need to write. And to write, you need ink. Here's what the Egyptians figured out. Burn something until it becomes carbon soot. Mix the soot with tree gum and water. The gum acts like glue. When the water dries, the carbon stays stuck to the papyrus. This is carbon ink. It's brilliant. The carbon is literally just burned organic matter. And carbon doesn't fade because it's already been destroyed by fire. You can't destroy it twice. But there's a problem. This ink sits on the surface. It can flake off. It can be scraped away. So scribes in Rome needed something better, something that would bite into the writing surface and never let go. This brings us to iron gall ink. And this is where chemistry gets weird. Take oak tree galls. These are tumor-like growths that form when wasps lay eggs in oak trees. Crush them up. They're full of tannic acid. Now add iron sulfate, which you can get from rocks. Mix these together with water and gum arabic. At first, the ink looks pale, almost invisible. But then oxygen from the air reacts with the mixture. The iron and tannins combine, and the ink turns black. Here's the strange part. This chemical reaction continues after you write. The ink actually bonds with the fibers of the paper or parchment. It doesn't just sit on top. It becomes part of the surface itself. You can wash the paper and the writing remains. You can scrub it and the words survive. This ink is so permanent that we can still read Roman documents written 2,000 years ago. But it gets stranger. Iron gall ink is acidic, very acidic. Over centuries, it eats through the very paper it's written on. Medieval manuscripts sometimes have holes where letters used to be. The ink preserved the words but eventually consumed them. Permanence destroyed by its own chemistry. This leads to an even stranger consequence. Different inks create different problems. Carbon ink fades in sunlight. Iron gall ink dissolves its own substrate. Early printers in the 1400s needed something that would stick to metal type, transfer perfectly to paper, and dry instantly. None of the existing inks worked. So they invented oil-based ink, linseed oil mixed with soot and resins. This ink was thick. It clung to metal. When pressed onto paper with thousands of pounds of force, it embedded into the fibers. Then it oxidized and hardened like paint. This ink made the printing press possible, which meant that for the first time in history, thoughts could spread faster than people could travel. But there's another piece to this puzzle. Different colors require different chemistry. Black is easy. It's just carbon or iron compounds. But blue, red, purple? Each color comes from a different source and requires different chemistry to make it permanent. Ancient purple came from sea snails. 12,000 snails produced enough dye for one toga hem. Royal purple was expensive not because people were greedy, but because chemistry is hard. Blue came from lapis lazuli, a semi-precious stone ground into powder. Red came from insects, cochineal beetles crushed by the thousands. Each color represented hours of labor and rare materials. And here's where things get really weird. Some inks were invisible. Write with cobalt chloride dissolved in water and you see nothing. Heat the paper and the words appear blue. Spies use this. Secret societies use this. The chemistry of invisibility became the chemistry of power. What does this actually mean? Ink isn't just colored liquid. It's humanity's attempt to defeat time. Every ink formulation is a small war against entropy. We're taking materials from the world and recombining them in ways that don't exist in nature, specifically to make our thoughts outlast our bodies. Think about it like this. The thoughts of Plato still exist, not because his brain exists, that's been dust for 2,400 years, but because someone mixed soot with gum, and those carbon atoms are still arranged on papyrus in patterns that encode his ideas. The ink defeated death, not Plato's death, but the death of his thoughts. Modern ink is even more bizarre. Ballpoint pens use ink that's basically paint. It's so thick it shouldn't flow, but tiny balls rotate and pull the paste onto paper through sheer mechanical force. Gel pens use pigment suspended in a water-based gel with polyethylene glycol. It flows like liquid while writing, but becomes solid afterward. Printer ink is a nanomaterial suspension. Particles so small they behave more like smoke than liquid. And each formulation exists because of a specific problem we needed to solve: permanence, color, speed, control, reversibility. We invented thousands of different inks because we had thousands of different ways we needed to capture thought. In practice, this means every word you've ever written involved chemistry you don't think about. The grocery list on your fridge, the signature on your mortgage, the note you left for someone you loved. All of these required humans to transform rocks and plants and insects into thought-capturing liquid. For us, living today, this seems simple, but we're standing on top of 4,000 years of chemistry. Someone had to discover that burning organic matter creates carbon. Someone had to figure out that oak galls plus iron makes permanent black. Someone had to realize that heating cobalt compounds makes invisible words appear. Looking forward, ink is evolving again. Electronic ink uses millions of tiny capsules filled with black and white particles. Apply an electric field and they rearrange. The particles stay in place until the field changes again. This is ink that rearranges itself, thoughts that can be written and unwritten infinitely. The truth is, we still don't know what forms thought capture will take in the future. Maybe we'll encode information in DNA. Maybe we'll write with light on quantum substrates. Maybe we'll find ways to preserve thought that don't require physical substrates at all. But we do know this. For almost all of human history, thoughts died with the thinker. Then we learned to burn things and mix the ash with tree sap. That small act of chemistry changed everything. It made history possible. It made civilization cumulative instead of cyclical. It let humans who lived thousands of years apart have conversations through symbols on surfaces. We don't fully know what ink will become. We can't predict what new substrates or chemistry will invent. But probably, as long as humans have thoughts worth preserving, we'll keep finding new ways to make the invisible permanent. For now, every time you write, you're participating in an act of chemical defiance. You're betting that patterns of molecules can outlast the pattern of neurons that created them. And for 4,000 years, that bet has paid off. That's pretty extraordinary when you think about it.